Ciesielski 呢，他是我们的老朋友，他是在西耶西夫大学，他跟那个 Professor Dick Johnson 做，他在那边毕业了，他在那边做研究，也做了很多年了。How many years you already did research with Dick? More than 10 years?
Oh, maybe 20.
20? 哇，很棒的这个他这个就是研究也好，跟Dick Johnson做了将近20年，所以是Dick Johnson教授的左右手。所以很多资料尤其是处理太空还有处理很多相关的资料分析，他都会把它写。从后来后的资料到 Sysmac 的资料到现在我们在做实验的资料，他都负责太空的 quality control 还有太空的做这个热量能量的收支的分析，所以研究做得非常好。所以等一下如果有问题的话，可以问他。好，welcome Dr. Ciesielski. Then we keep on.
Thank you, Peter. Thank you for inviting me to come here this afternoon. Before I begin, I just want to give you a couple impressions from Taiwan that I will take back with me to the United States. The first impression is I've just been overwhelmed by the hospitality and kindness that many people have shown me here, even strangers. Quite remarkable to me. And secondly, how hard people work in this country. I don't think they work that hard in America, but it's really left a great impression on me. So I say keep up the hard work, but enjoy life too.
Is this your first time to Taiwan?
No, this is my third time. I came I came last November for a planning meeting, and then I came in April to help out with a sonde air comparison study. And they picked me up at like 3 in the morning. Maybe some of you were involved, and I was surprised that everyone was getting up so early to do this study. So it left quite an impression on me. So this talk here is on identifying problems that we find in sounding data and trying to correct them. Now, this type of work, it's like doing dirty laundry. I don't know if you understand that. So when you go out in public, you look good. Now, Dick Johnson and I, when we use the sounding data, we like to look at conservative budgets. You know, we talk about Q1 and Q2. Maybe some of you are familiar with that. Apparent heating and apparent drying from some of your nice work. That's what we like to do, but in order to get to that point and have good budget analyses, we need to correct the data first. And so it's like doing the dirty laundry in order to get to that point where you trust the data. So why do we need to be concerned about this in TIMREX? Does this one work? Or do I use the mouse?
Yep.
Okay. So this is the large-scale sounding network for TIMREX. And the color coding of these circles, each circle here represents a sounding site. And the color coding of the circles indicate the type of sonde that was used at each of these sites. So one thing you notice right away is that we're using several different types of sondes in TIMREX. The black dots are Vaisala 80s sondes. They tend to be the oldest ones. They're used at Hualien and the Air Force sites. And then you have the Vaisala 92. It's these gray dots. Grau system is from Germany. It's used at the ship and also at Layag in the Philippines. And actually this site now we're getting 2 sondes a day from this site. Taiwan provided them with the sondes. There's the Japanese Meisei system is being used at 4 sites. This is actually a Japanese island here, but these 3 other sites that are part of TIMREX network. And then China uses the Shang system. So we have all these different sonde types, and they all have their own biases. cross-section across the northern South China Sea, you see that each of these different sonde types would be involved in this cross-section. So if we want to do a cross-section of relative humidity, we need to make sure that all these systems have reasonable relative humidity if we're going to get a good analysis of the field. Please feel free to jump in any time or ask questions along the way. So when we look at sonde and begin to examine some of the problems, we see that the temperature biases from one sonde type to the next are relatively small, on the order of a degree. And wind measurements have improved dramatically with the use of GPS technology. On the other hand, moisture errors and sound data dominate the data issues that we generally deal with in our quality control efforts. This is a sounding launch that was taken on May 18th, so just a few weeks ago, by Dr. Liu. And here he compared, he took a 92 system and he compared it to a Vaisala 80 system. So the Vaisala 80 system is the system that's used at this site, the Pingdong Air Force Base. Is that correct?
Yes.
Okay, so that's the blue line, and also this dash line. You can see the temperature difference. The two curves on the skew-T plot, they almost are the same. You really can't see much different. But you see a large dry bias in the Vaisala 80, especially near the surface. And since convection is very sensitive to low-level humidity, this is a real problem that needs to be corrected. So this is an example. So today's talk will focus on identifying the moisture biases, relative humidity biases that we find in sonde data, and how do we correct them. I like this picture. It shows many different modes of convection that are going on. And the basic issue here, when we're trying to correct the data, is to get an accurate description of the atmosphere for input into diagnostic models. That's what I like to do, Q1 and Q2. And also for modeling studies of the monsoon. So convection in atmospheric models, namely its location and intensity, is quite sensitive to the low-level moisture field. And if convection is incorrectly simulated, this affects the distribution of latent heating. And because the balanced dynamical response to latent heating is particularly sensitive to the vertical profile of latent heating, getting the correct simulation of the circulation is dependent on getting the convection correct and getting the moisture correct. So correct moisture leads to correct convection, leads to a correct latent heating field, leads to a correct response and energetics. So it really starts with getting the basic fields correctly. So initializing models with the correct thermodynamic fields is crucial for accurate forecast and dynamical diagnostic models. So I'm just going to discuss some of the ways we can identify moisture biases in sounding data. First, you can calibrate it with other instruments. And a good way to do this, and I'll show an example, is to use precipitable water from GPS receivers. And also, you can get it from the satellite sounders, like AMSR-E. And also, you can retrieve precipitable water. And then you can do inner comparisons with reliable sondes. A very reliable sonde system, which is considered the most accurate we have, probably for laboratory tests, is called the Snow White system. It's based on this chilled mirror hydristor. And then you can look at characteristics of the boundary layer. The lowest few hundred millibars of the atmosphere contain the majority of the moisture. So examining the moisture in the boundary layer is one way to identify some humidity biases. And then examine convective parameters from one site to the next, like precipitable water, K, SIN, LCL. And then look at the frequency of saturated layers through the depth of the atmosphere. It turns out in TIMREX that I've been looking at the various sites. In 4 sites have not shown any saturated layers in the last 3 weeks. 4 sites. And this is an area which has frequent convection. So they're not showing any clouds, if you were to believe those soundings. So that's a serious problem that needs to be corrected. So now I want to just show a few results from this paper. Very interesting paper by Wang and Zhang, and I'm not sure I'm saying that right. But what they did is they compared the precipitable water from 14 different sonde types around the globe. I didn't even realize that there were that many sonde types. In the United States, they used 2 sonde types, Vaisala 92 and something called a Ciesielski-Identifying or a VIS system. In Taiwan, we saw that they used 4 different types. The GPS precipitable water is accurate to within a few millimeters and has a small negative bias. So it's an excellent reference for precipitable water from sounding data. So when I talk about computing precipitable water, this is what I mean here. Integrating the water vapor mixing ratio over the depth of the atmosphere. That gives you the integrated moisture in the column or precipitable water. This is a key diagram from this paper. So what they're doing here is they're comparing the precipitable water from the sounding data to the GPS. And they looked at 169 sites in over a 10-year period. So whenever you had sounding data and GPS located within 50 kilometers and within a few hours, then they were able to do this comparison. So each of these dots here on this plot represent one site, and it shows the difference between the sounding precipitable water and from the GPS. If it's below 0, it means that the site has a negative bias. The sonde has a negative bias. And so all these types here represent a capacitive type of measurement of humidity. So these are all the Vaisala systems, the Vaisala 80A. Those are the ones that are being used at the Air Force sites in Hawaii. And then you have Vaisala 88, 90, 92s. This is the most recent Vaisala system that's being used at several of the sites. I believe your system uses this one. So you can see this represents the mean and standard deviation for these 3 types, the capacitive, the carbon hygrister, and the gold beater skin. These are the Shane systems that are used in China. So you see that capacitive sondes, they tend to have a dry bias compared to the GPS precipitable water. And these carbon hygristers, they have a moist bias in the mean, and in the gold beater skin, they also have a moist bias. If the dot is colored red, that means that it's significantly different. The difference is significant from 0. So you see most of these Vaisala 88s, they have a significant dry bias. But there is variability between the sondes. You can tell that as the sonde systems have improved, that the biases have become smaller. So that's encouraging. Also in TIMREX, there's some raw sondes, but in this plot, they were only able to do this comparison for one site. And there was very little bias. And there's actually 2 MESAs systems here. They both show a dry bias, those MESAs systems. Yes?
What's the red means? Different station, right?
Each one of these is a different site. And those bars represent the standard deviation.
So I'm kind of curious, because you say the improvement, the improvement is due to they are limited sample.
Yeah, there is a more limited sample.
Right, if you put the 80A on the right side, you don't see much difference. So I just don't understand what the sampling issues. Depends on the sampling issue.
Yeah, that's part of it. Yeah, there's a much more.
You have much more sampling.
There's much more
So
sampling.
you know the bias quite clear, right?
Yes.
If you
Yeah.
are less sampling,
Right.
your sampling is on the right side.
Yeah, there's fewer sampling here. Yeah, that's right. But these have, you'll notice the standard deviation here is smaller at these sites than the sites. But yeah, there's a difference in sampling. But we feel that the instruments have improved over time. Now this is considered one of the better systems, the Vaisala 92s. The ones that are being used in Timex, you can see that these pick up saturated layers. Whereas at the sites that use the 80 vein, you never see any saturated layers in those. This is from another study, a very recent one. This was by Yoniyama in 2007. In this study, they had 3 sounding sites located near the equator in the eastern Indian Ocean. And this study was to study the initiation of the Madden-Julian oscillation. But they had one ship that was located on the equator that launched Vaisala 92 sondes along with Snow White sondes. So this Snow White system is one that's considered a reference sonde. So these were from 14 near noontime soundings. And the red line here represents the difference between the Vaisala 92s and the Snow White system. So you see that there's a rather significant drive ice, fairly small at the surface, but it increases with time up to about 40 to 50% here near the top. And this line here represents a polynomial fit to that red line. So they're using this line here. They use that as fit as a correction to their sonding. This green line here is from a study that was about a year earlier, where they did something similar. They compared 92s to Snow White. Well, that study showed a much more significant drive ice, like 10% in the boundary layer. In Yoniyama's study, they said they don't know why there's this difference. Maybe Vaisala has made some improvements between this time. I don't think we really know. Also, Baumel's study, this green line, was conducted over land in Costa Rica, where this study here was conducted over the ocean. Maybe that's some of the difference. And you see there, just because there's only 14 launches, the standard deviation here is rather large. So I guess my point is, if you're going to do an intercomparison study, you want to have a large sample so that you can decrease the standard deviation, make sure you have been established a statistically robust correction. So the other thing they did in their study is they compared their data. They also had a GPS receiver on this ship. So they looked at the diurnal cycle. They launched sondes every 3 hours, so 8 times a day. So this shows the diurnal cycle of the RS-92 minus the GPS. So again, if it's below 0, it means the sonde has a negative bias. So this again is precipitable water difference. And you see that during the daytime hours, the 92 system is showing this dry bias. The bias is fairly small during the nighttime hours. So this, after they did their correction, this is what it looked like. They were able to improve that dry bias by applying that correction. So the point here is collocating GPS receivers with sound sites helps us to identify the moisture biases and also to validate the correction. And they say in Wang and Zhang's study, they recommend that the sonde and the GPS be located within 50 kilometers of each other to be able to do these intercomparisons. This flies from a WMO study that was conducted in 2001. There they intercompared 6 different sound types. The Vaisala 80, 90, the Graal system, a modem system, along with the Snow White. And this shows that they did this intercomparison in a wide variety of conditions, day, night, rainy, dry. So you need to do that because the the bias could be different depending on the conditions that the balloon is being launched. Just this gives an example of one of the launch setups that they use, where here they compared 5 different types of sondes in the same launch. Rather complicated. This here shows the average vertical profile from this study. Here these pink markers represent what the Snow White system found. And I don't want to go into a lot of detail. You can see that compared to this Snow White system, the pink, you can see some of the biases in the other sonde types. They all seem to be drawing upper levels. This red line is the Vaisala 80. It's showing this low level of dry bias, and this Gauss system has a noise bias. Just to give you an idea of how these biases are identified. So I want to talk just briefly how we've seen these in some of past experiments. So I'm going to look at 2 experiments that I worked with data, Toga Core, and that's where Dr. Lin and I, we first met each other working with data from Toga Core, and also NAME. NAME is a recent experiment, North American Monsoon. This experiment here, I'm going to show you the large-scale sounding network for it. This experiment lasted for 4 months. In all these sites here, launched balloons 4 times a day. So this fellow here was located at Nauru. Were you there all 4 months?
1 month. But that is still in the teacher.
Okay. Yeah.
Probably 4 months.
So this lasted from November 92 to February 93, 120 days, launching 4 times a day. The color coding of the surface here indicates the sonde types that were used. So you had this type sondes used along 8 to 10 north, and the rest of all these other sites farther south there. This means intensive flux array, outer sounding array, large scale array. So all the sounding sites in this intensive flux array were Vaisala systems, whereas these were VIS systems. So someone tried to use this data of sometime after experiment, maybe a year after experiment, to initiate convection in their model, and they said they couldn't do it. This was Ed Zipser in his group. So he started to look into the data. He says, something's wrong here. And this is what, when we began to realize we had serious problems. This is the specific humidity difference between the surface point and the humidity average in the boundary layer, or the lowest 50 millibars. And the red bars, each bar here represents a sounding site in Toga Core. The red bars are Vaisala sites, the VIS bars are VIS sites. So they're ordered here from smallest gradient to largest gradient. Well, you'd expect, based on Monin-Obukhov similarity theorem and some aircraft flights, that this difference between the surface and boundary layer should be about between 1 and 1 1/4 grams per kilogram. Now I just want to point out here that the surface measure of humidity is independent from the sonde. So this is independent, and then this from the sonde, the surface point, and this is from the sonde data. And you see this scatter. Most of the VIS sites have very small or even positive gradients, and the Vaisala sites are all over the place. Here's Nauru. It had about 3, so it has some problems too. So when we saw this, we realized we had some issues. Here's 2 sites that are located quite close to each other, Vickers and Kapinga. You'd expect their specific humidity difference to be quite close. One seemed close to the range. This was a ship. The other one, Kapinga, was far off. So what happened? We realized there were problems. Vaisala got together with a group at NCAR, ATV division, and I just want you to notice the date here, 2002. The experiment was held in '93. So they worked on these corrections. I'm not going to go into details, but 6 different errors that they found in these sondes. So they applied that correction to these 8,100 some sondes, 29 sondes. And the viz, they also had errors, and they were corrected. And then, of course, it took them 10 years to do it. I hope we can do TINREX a little quicker than that. So after all those corrections were applied, each sonde was visually inspected, and obviously that data was sent to listen. So this is about over 11,000 sondes that were visually inspected. And I understand that the person who did this, he quit after he did that. He had it. So this here shows the magnitude of the humidity corrections for the 3 sonde types that were used. Let's just focus on this one now. So these 2 lines represent the mean over all the sites, the mean relative humidity profile, and this is computed with respect to ice, I believe. So the black line is uncorrected, the red line is the corrected humidity, and this plot here shows the difference between the 2. So the scale's a little different. So you can see that the correction increased the relative humidity in these Vaisala 8 sondes about 5% at low levels and greater aloft. In terms of specific humidity, it's about a gram per kilogram increase in moisture. So some sites it was more, some sites less, but this is the average over all these Vaisala 8 sondes. Now this shows what happened at the VIS sondes when they applied the correction. It actually went the other way. It actually decreased the moisture in the boundary layer about 3% or about a half gram per kilogram. So these had a dry bias that was improved, and these had a moist bias. They were dried out. So I want to show you a few of the impacts that correction had. And this is on some diagnosed properties of convection. This is K, uncorrected values for the 3 sonde types and corrected values. Just look at the difference between the Vaisala H and the VIS sondes, uncorrected K. Huge differences, almost a factor of 2. After the correction, they were almost similar between the 2. SIM, very large differences. Afterwards, much more similar. So based on these uncorrected values, you might think that it would be difficult to trigger convection over the intensive flux array where you had these sites because K's were so low and SIM so high. But after the correction, you get a much different impression of the convective, where convection might break out. So the K and SIM and the corrected value, it gives you the impression you might have similar convection everywhere over the warm pool. So the VIS sondes were here, the Vaisala sondes here. But this is a 4-month rainfall map. This is a GPCP precipitation satellite product. And it shows the heaviest rainfall was actually south of the equator. And this shows the diagnostic computed omega, a cross section between these 2 longitudes. So this goes from 10 north to 10 south. So you see the diagnosed vertical motion was actually a maximum around 3 north, where you might expect it. That's where this heavy band of preset cut across that cross section. So to look at the impact of that humidity correction in more detail, we use a cloud model to compute the convective mass flux. And again, this is a cross section from 15 north to 15 south over this longitude band. It cuts right through the intensive flux array. In the uncorrected data, the largest convective mass flux is right here around 8 north, right where all those VIS sondes were that were too moist. When you correct the data, the largest mass flux is now south of the equator. And this just shows the difference in mass flux between uncorrected and corrected. So IOP mean convective mass flux peaks at 8 north in the uncorrected analysis. And then it's just south of the equator in the corrected. And this agrees much better with observed rainfall. Now, the reanalyses, ECMWF and NCEP, they use the uncorrected data, and they did the reanalyses. Where do they get the maximum rainfall? I don't show it here, but they got it at 7 North. So this just shows the sensitivity to convection and where rainfall is going to occur if you use uncorrected data. So this shows the sounding network for the NAME experiment, North American monsoon. This was held in July and August of 2004. So we do have a monsoon in North America. You actually get surges of moisture that come off the Gulf of California, and you can get heavy rainfall over the deserts of Arizona and the Southwest. There's actually a mountain range called the Sierra Madre Occidental that cuts through here. It doesn't show up very well. The shading here is the topography. So there's a mountain range, and typically around noon, you start to get the convection firing here, and then it moves off towards the west as the day goes. So in this, again, the color coding of the circles indicates the location of the sounding sites. NCAR put 4 special sites here. 3 of them were ISS sites. And all the black dots represent sites that the Mexico government supported. I call them SMN sites. All these systems, all these sites use the same sound type, the Vaisala 80H. So it's a grade. So we should find the differences between these sites should be real. Well, that wasn't the case. Okay, again, I'm showing differences here between the surface specific humidity and the first point above that. That could be, depending on the ascent rate of the balloon, that might be 5 or 10 meters above the surface. So again, these are independent measurements. That comes from an independent surface site. This comes from the sun. This is the surface point. That's the first point above it. The difference should be small. At the U.S. sites, this is the mean. It was small. This is just a scatter diagram. So you see it rather small. The NCAR sites, it's fairly small. Then you see the SMN sites. That difference is above 2. And this shows what that surface gradient is at the different SMN sites and the NCAR sites. The NCAR sites are all fairly small, below 1/2, and the SM sites are showing very large change between the surface value of moisture and the very next point up, which might be 5 or 10 meters. And here we also looked at the frequency of saturated layers at these different sites. The NCAR sites had between 1 and 5% of their layers in the 5 millibar data saturated. The Mexican sites had almost no saturated layers. And this is in a region that had daily convection. So we know something is wrong. This is just an example of a skew-T plot showing one of these cases where you have this huge jump in dew point at the surface. So this comes from an independent surface measurement. That's the first point in the sun. Here's a dew point decrease of like 16 degrees or something. So we saw this in the field and we tried to get someone to try to fix it, and they said, oh, just be happy they're launching the balloons. And also, the precipitable water for this sound was only 9.4. So very low. That's just an example of what's, bad data might look like. This is an example from Timrex. This is a sound that was launched on the 13th of May, and this is at Pink Dome. Again, you see this large jump in the specific humidity, actually the dew point at the surface. And this here, the sound launch time was, 13:03. So that's 11 a.m., is that correct? Yeah. So you see around, the temperature is well mixed, as you would expect during the day, but the moisture is not. Very suspicious. Here's another weird sound, incorrect sound that we saw in the name. Here we see it saturated over great depth. So what happens here, this is in this Vaisala 88 system. The system actually, when it goes through the cloud, it gets covered with ice, and it stays that way. The ice doesn't melt off. And so it shows saturation over great depth. There was a GPS receiver just 5 kilometers away. The sonde had a precipitable water of 62.5 millimeters. The GPS receiver was only 45. So this really shows the value of having a GPS precipitable water estimate nearby. Now the new 92 systems, they actually have a heated humidity sensor, so you don't get icing anymore on the humidity sensor. And that's an improvement in the 92. We look at the convective parameters. So the red ones are the SMN sites, and the black ones are the NCAR sites. Just look at the difference between these three sites, Kino Bay and Palme and Los Mochis along here. Look at the differences in precipitable water. You'd think this site would be somewhere in between. And the Cape, look at the differences in the Cape. So we looked at all this information and we realized that these Mexican sites had a serious dry loss, yet they use the same type of sonde. So we asked ourselves, why? Why would this happen? So the NCAR sites, they had well-trained personnel. They all had to go to NCAR to get trained before they could launch the balloons. They used the latest sonde software. The sonde NCAR technicians, they visited each of the NCAR sites during the field experiment to troubleshoot any problems that arose. Whereas the SMN sites, they were staffed by Mexican civilians. So the Mexican government actually just hired families to take these extra launches. These civilians were not meteorologists, they weren't trained. They probably used 4 pre-launch operating procedures, and we don't know. We think their sonde software may have been outdated. So a combination of all these factors, we think, caused the problems in this experiment. So this just summarizes the ways to identify humidity biases. You can do it with calibration against other instruments. For example, precipitable water from GPS. But this only gives you, it doesn't give you the vertical structure, it just tells you the problems in the mean. Then you can use intercomparison with a reliable system like Snow White. But the Snow White system is very expensive. It's about 5 times expensive as the other system. You can look at characteristics of the boundary layer. You can examine convective parameters and look at frequency of stabilizers. So now I'm just going to briefly mention a few ways that we use for correcting the data. Well, you could conduct a series of laboratory tests, as was done with the Toba core data, where they identified all these problems. And June Long has a paper in 2002 where she talks about all the errors that were found in the Toba core data. And these corrections take the form of these higher order polynomials that are functions of temperature and moisture, pressure, the age of the sun. The older the sun gets, the greater the dry bias, and also the time of day. You can use statistical methods such as CDF matching, and I'll briefly show this. This was used in the Emma experiment held in Africa a few years ago, and we're using that technique and name to correct the data. And then you could conduct intercomparison launches with a reliable system, such as the Snow White or the RS-92, to find out what these biases are. So again, this was what the dry bias looked at the SMN sites. So here I'm comparing the mean profile from the Palme. This is RH. This is averaged over 109 sondes. And I'm comparing it to some weighted average of these two. And this is the difference. The SMN site in Palme has this large dry bias, about 10% in low layers, about 30% on off. So we want to get rid of this dry bias in the Palme, so we use this technique called Cumulative Distribution Function Matching Method. Now I'm not going to go into the details, but basically you assume that the statistics of the two sites, the statistics of the moisture should be similar. So you plot a probability distribution function, or cumulative distribution function, and you try to match it between the two sides, and that gives you a bias. And you do this for several different temperature bins, and you construct a correction table. For example, if we know that the uncorrected humidity at Empalme was 30% and the temperature was 10 degrees, this would say we need to correct it by about 9%. So that's another method for correcting. Of course, Yoniyama, I mentioned his paper. He fit this polynomial to this mean difference. So he came up with the second order polynomial, and he used this as a way to correct his sondes and his experiments, and found that the improvement was considerable. So what are we going to do for Timrex? That's the question at hand. So we have all these different sonde types. Some of them we know have serious dry biases that we've seen over the last 3 weeks. These 4 sondes here have not shown a saturated layer now in 3 weeks. So we know they have a significant dry bias. Well, one thing we did is we had a sonde intercomparison study in April, 15th and 16th. Were any of you involved in that? Okay, because I know there were several students there.
Out in the field.
Well, they're out in the field. Okay. So Dr. Ho-Shung Lin, is that right?
Yeah.
He came up with this basically structure to launch 3 different sonde types. The Vaisala 92, the Grau, and the Mesa. So we only had 4 launches. This was just to give us an idea if there was a sonde bias. And it turns out, yes, we did find it. So we used the parachute so it didn't fall down on anyone's head. This is actually a picture taken of one of our launches. This shows an example of skew T-plots for the afternoon launch on one day and the morning launch. And so these are the 3 sonde types, the 92, the Meissei system, and the Grau. You can see the temperature curves. They agree fairly well, within about a degree, but some significant differences here in the dew point at low levels and aloft. The wind differences were quite small between these 3 systems. Of course, we launched them all on the same platform, so you'd expect them to be small. I won't go into details here. This is the relative humidity profile for these 2 sonde launches. And the point here is the 92 is the only one that reached saturation. There was a cloud layer at this time. So the Vaisala is the blue line. So it reached 100% relative humidity, but the other systems did not. So you can see these differences between the moisture and here I really expanded the temperature scale. It shows the temperature differences. But basically they're within a degree. They're similar from day to night, and they tend to increase at upper levels. I'm not sure we understand this, but we hope to. We're going to study this data more. But we only have 4 intercomparison launches, but it gives us an idea that yes, there are some biases. So in summary, results from the intercomparison study and other intercomparison launches, they're actually Professor Ching. Yeah, thank you. He's going to launch a series of intercomparisons between the 80 system and the 92 system at Pingdong in the next few weeks. There was no 80 system. The 80 systems are not portable. That's why we couldn't include them in this study. So hopefully we're going to do some more comparisons here during the fill program, and we'll use this information to develop some correction methods to improve the Timrex sounding data. We'll also use GPS and satellite-based specific water to help validate these corrections. And then, just this point I wanted to make that the corrected upper air sounding should provide a scientific community with a legacy data set. That is, I mean, one of lasting value that will be used for years to come for the study of heavy rain events in the monsoon environment. And here's a picture of Ho Shung Lin, and he's explaining to the students, I think he's saying that if you do it right, it's going to go up. And I'll end this with, if there's any questions, this was actually a student who helped out at one of the morning launches who was obviously exhausted. And I was on a jobs on flight earlier in the week, and this is a picture that I took actually from the airplane. Yeah, it's just amazing. This is just off the coast of Taiwan. Yeah. Isn't that beautiful? What just a classic handle type. Thank you.
Any question?
Yes.
You mentioned in the Mexican example that United States
Yes.
account a large portion of
Yes, exactly.
viruses. Is that one of the possibilities any environmental or viruses?
Well, there could be several reasons. They could have been taking these instruments out of an air-conditioned environment and then launching it without letting them ventilate properly. So when you take the sun out of its package, you have to let it ventilate so that it's measuring the ambient air and not the air that was being inside the trailer that it was being stored in. So that's just one example. It may have been the software that they were using at the time. We haven't been able to track down that. So we're thinking that it's probably 4 pre-launch procedures that were used at these sites. So we really encourage that all the students go out in the field, that they are well trained. Another issue may have been you need to, before you launch a sign, you need to compare it to an independent surface measurement to see if the sun and the surface measurement at that place and time are measuring similar. I don't think they did that in this other experiment, but they are doing it in May. So that really helps that surface in the comparison. And if the difference is too large, you don't use the sun. And typically about 80% of suns are not used if you do that in a comparison. Does that answer your question? Okay.
Any other question?
You need to explain anything in Chinese? Feel free to I commend Frank. He sat through this talk at least twice now. Yeah. Like I say, it's dirty laundry. Yes.
So what kind of major lesson was learned from the previous two experiment when you doing the things for the, say, for example, you said from the blackboard.
Yes.
My second question is, to what extent what our experience can be quantitatively be transformed to the next events, when they're doing the similar exercise.
Yes.
Quantitatively, not quality. Of course, qualitatively, of course, everything will be, all the experience counts. We can transform, but quantitatively.
Yes. Well, we're going to do this inter-comparison study at Big Dome. He's going to launch a number of songs. We're going to come up with hopefully a correction that will be used and applied to the songs at all the bisolid 80 sites. So hopefully that will take care of the problem there. But there's still a small bias in the 92s. So what we need to do there is really to compare the precipitable water at all the sites to the precipitable water, from the SONs and the GPS. Because Taiwan has a very good network of GPS receivers that we can look at that. So, hopefully that will help us to identify problems. Some of the lessons that we learned is that we need to be aware as the experiment's going on of these issues. In Toka Core, we just assumed everything would be fine, that there would be no problems. What I think I learned from my experience is you need to look at the data as it's coming in and begin looking at these look at saturated layers, look at changes of the dew point from the surface to the next point to see if these problems exist so that you can do something. Well, one of the things that we've done is I kind of tried to make people aware of things that we saw as the data was coming in, and that's why they're going to do this in their comparison study of Pingdong here in the next few weeks. And the other thing that we learned is make sure you have trained observers. And I think Taiwan has done a very good job of trying to train their observers. And it's important that the observers take notes when they're launching the sondes. If they see anything particular going on, to make note of that. So when we go back and do the quality control, we'll have this information. So those are some of the things that I've learned over the years is, one, there's probably going to be problems, so try to catch them early so it won't take 10 years to correct your data. I hope we can get a corrected data set, maybe within a year. It's going to take time. It's not an easy thing to do, but at least it won't be this 10-year period. Maybe we're still correcting the data. It's only been 4 years. That's because I'm doing it. I'm involved in other projects. But you want to get the data corrected quickly because people want to start doing their, they want to do their analysis. They want to run it in the models. And you know, the thing is, it's kind of scary. They just want the data, right? You know what, Ben? Give me your data.
Yeah, that's right.
They don't care about really the quality control, but it's very important that it gets done right.
Yeah.
So.
I guess I create a comment just made. I think it's very important. Since a camera, we expect a lot of money. So in order to understand state that from scale, all these sort of things, you have to have a very, very well organized collective. So, radar bar, same with operators. And I believe operators are, which is very crucial by the environmental conditions, condition to stop running. So in this condition, with some of labs, uncorrect researchers in this lab. So I think this ought to be done as quickly as possible. This problem is one of the top priorities in our opinion. The scientific community here in Taiwan. I think we need to get completion about the report stuff, indicating the seriousness of this problem. And we cannot ignore the fact that this lead us to ground level.
Good point, yeah. And I don't know who's in charge of that, of correcting all this. And I've told others that I would be happy to help and advise, but it's going to be a big task. So,
Yeah.
yes, maybe,
we need a group of people to
yeah, it should be a group effort, I think. So.
Well, in this case, how bad is the systems?
Yeah.
Not bad, except the Donggang station.
Yeah, there were humidity biases in Sysmex from one site to the next, but you know, we didn't look at that in great detail. We actually computed the budgets with the data after we did some quality control, and they came up quite reasonable. So we were happy with that. Yeah, you worked with Sysmex, so I think Sysmex did a pretty good job.
Yeah, it's just like the Vaisala son already upgraded from the 80 to 80H.
Yeah.
So 80H is
Better.
Yeah, better. Right.
Well, thank you for your time and attention.
Any other question? 有没有同学要问问题？ OK， 这个就是告诉大家说，放太空虽然是简单的一件事情，但是没有好好放的话，也是会出大的错。最后算了一大堆东西，可能就是一些小误差，最后